In this example here, we have a stress-strain graph. Calculate the Young's modulus using the data given. So Young's modulus is stress over strain. And if you look at the graph, stress on the y-axis and strain is on the x-axis. So if we do change y over change in x, which is the gradient of this graph, we can get the Young's modulus. So changing y is, if you take from the very top, 200 megapascals, so 200 times 10 to the 6 minus 0, and the change in x is 0.4 strain there minus 0. And so that gives us Young's modulus of 0.50 gigapascals. Okay, now we have two lines here, one for wire A and wire B, and we're asked to compare the two wires. So the gradient of this graph represents Young's modulus, and you can see wire A has a higher gradient. So that means wire A has a higher Young's modulus, which means it's stiffer. So what that means is the material that wire A is made out of has a higher Young's modulus and is stiffer. However, if we make wire B a very thick wire, so like a large cross-section area, it could have a smaller extension than wire A. What this Young's modulus graph, the Young's modulus we get from these graphs, tell us is about the material that the wires are made out of. Sometimes you might be given a strain against stress graph instead of stress against strain. So in this case, you can still use a gradient, so y changing y over changing x, but y-axis is strain and x-axis is stress, so it's strain over stress, which is 1 over Young's modulus. So let's go ahead and calculate the gradient here. So changing y over changing x, and we get this value. To get the Young's modulus from this, we need to do 1 over the gradient. So if we do 1 over that, and we get the same Young's modulus as before. In this example, we're trying to calculate Young's modulus as well, but instead of stress against strain, we've got force against extension. So this graph alone won't be enough to calculate Young's modulus. We also need to measure the diameter of the wire and use that to figure out the cross-section area, which we're given here, 8 times 10 to the power minus 7 meters squared. We would also need to measure the original length of the wire. Once we have that, we can use the force extension graph, and hopefully remember the gradient of the force extension graph, changing y with changing x, is the stiffness constant. So here 16 over 0.8, that gives us a stiffness constant of 200 newtons per meter. And then Young's modulus can be, using this equation, stress over strain, where I've rearranged it already. If you look at that very carefully, force over extension is in that equation. It's right there. And force over extension is the stiffness constant, K. So I'm going to replace that with K there. Okay, so that means once I've got the stiffness constant from the gradient, I can put that into this equation and figure out the Young's modulus. So stiffness constant is 200 times the length, which is 2 meters, over the cross-section area, which we calculate using the diameter of the wire, and we get the same Young's modulus as before. Here we have a stress against strain graph, but we've stretched it so much that it's actually curving towards the end there. So keep in mind, stress is proportional to force and strain is proportional to extension. So you get the same pattern if you plotted those graphs as well. So initially we're loading, we're adding weights, and we added so much that is actually bending at this point here. So meaning the is no longer directly proportional, it's no longer a straight line. So that's called the limit of proportionality, the point beyond which stress and strain are not directly proportional. Also, force and extension are not directly proportional. The same applies there. Okay, and there's another point here where in this region, where there's another unique point called the elastic limit, which is different from the limit of proportionality. The elastic limit is the point beyond which the material no longer returns to its original length. We can say that the object has undergone plastic deformation. So we can only see this if we start taking the weights off. So if we unload, if we remove the weights off the spring and we unload it, it returns not to the origin, but to a point where there's some strain or some extension. So you can see here around 0.15 strain or extension. So that means it's not returning to its original length.